Welcome to our online lecture, Introducing Hypothesis Testing. So in this lecture, we're going to call it part 1 of chapter 7. We're going to cover hypothesis testing, and we're going to do a one-sample hypothesis test for means with a known standard deviation or an unknown standard deviation and a proportion. And in the next set of lecture slides for chapter 7, will be 2 sample hypothesis tests, analysis of variance, otherwise known as ANOVA, and a chi-squared test for independence. All right, so statistical inference allows us to infer something about the population from a sample. It includes confidence intervals, which we've already covered in chapter 6. That is where you estimate a population parameter with a range of values. And it also includes hypothesis testing, which allows you to make a decision about the population parameter. We can answer questions with hypothesis tests similar to, did a new assembly method decrease average assembly time? Did an advertising campaign increase average sales? Are the fraction of on-time deliveries greater than 90%? Is the proportion of voters who will vote for a candidate less than 50%? We can answer all sorts of questions with hypothesis tests, but those are just a couple basic ones. All right, so the hypothesis testing procedure basically says, based on sample data, what can we infer about the true value of the population parameter? The parameters for hypothesis tests are commonly means, proportions, and standard deviations. So let's think about the legal system in the United States. What is assumed in the legal system? When somebody goes to trial for a crime, let's say, we say we're going to assume they're innocent until proven guilty, right? And then we have this assumption of innocence, and the prosecutor's trying to prove guilt. What are the decisions that the jury can make? There are only 2 decisions, either guilty or not guilty, all right? In hypothesis testing, that assumption of innocence is called the null hypothesis. Notice the notation over here, that H sub naught. In the legal system, the null hypothesis, the thing we assume until we find evidence otherwise, is innocence. The alternative hypothesis, the thing we're looking for evidence of, is guilt. Notice the notation for that, H sub A, or sometimes you'll see it as H sub 1. All right, so H naught is read as H naught, H null, or H 0. I call it H naught, and that symbolizes our null hypothesis. If your evidence, your sample data, strongly indicates the defendant is guilty, you reject their innocence and conclude guilt. If there's not enough evidence to indicate the defendant is guilty, we don't say that they're innocent, right? We just say we just don't have enough to conclude guilt at this time. So notice the subtlety there that's very important. We're not proving innocence. We're saying we can't reject their innocence. We cannot conclude that they aren't innocent. And this is exactly the way we're going to make our conclusions in hypothesis testing. Notice that when we do make a conclusion, either guilty, we found evidence for our research hypothesis, our alternative hypothesis, or not guilty, we just didn't find enough evidence for our alternative hypothesis. We don't ever say we are proving guilt or innocence. We don't use the word prove, nothing that strong in hypothesis testing. We're just saying we conclude. All right, so in hypothesis testing, the null hypothesis describes an existing theory. I always like to say it's what we have no choice but to believe until we find evidence otherwise. And the alternative hypothesis is the complement of H naught. It's what we want to prove. It's the research hypothesis. It's the thing that we're trying to find evidence of. Using sample data, we either will come to the conclusion to reject the null hypothesis and conclude there's sufficient evidence to support the alternative, or we're going to fail to reject the null and say that we have insufficient evidence to say that the null hypothesis is not true. We have insufficient evidence for the alternative. So notice that those are the only 2 decisions that you can make in a hypothesis test. We always conduct our hypothesis test under the assumption that the null is true, just like in the legal system, innocent until proven guilty. It's what we're going to believe until we find evidence otherwise. So we're going to use the sample data to determine whether the alternative is more likely to be true. Remember, statistically, we aren't proving the either one is true, and specifically, we're never going to say that we're concluding that the null is true. We're only going to fail to reject it. Rejecting the null hypothesis provides strong statistical evidence that the null is not true and that the alternative is true. What we want to provide evidence for is the alternative hypothesis. All right, so we've got one sample hypothesis test, and we're going to learn two. That is for a mean and for a proportion. And then we've got two sample hypothesis tests for the difference in means. We're going to do that for independent samples. We're also going to talk about the difference in means with a paired sample, and we're going to talk about equality of variances. Now, there are many other hypothesis tests out there. You can test for association, you can test for the slope and regression. There are all kinds of hypothesis tests out there, but we're just going to teach you these. Now, for any of these hypothesis tests, they can be lower one-tailed, upper one-tailed, or two-tailed. All right, so one sample hypothesis test. So we often compare a single population parameter such as mu or pi, the population mean, or the population proportion, to some constant number. We use a single sample of data in this case, and there are three types of alternative hypotheses. So you can either have the less than sign in your alternative hypothesis, the greater than sign in your alternative hypothesis, or the not equal to sign in your alternative hypothesis. Notice that when you have the less than sign in your alternative, we call that a lower one-tailed. When you have the greater than sign, we call that the upper one-tailed. And when we have the not equal to, we call that a two-tailed. When we do a hypothesis test and I draw the picture for you, you'll see why we call it one-tailed versus two-tailed. Now, another thing I want you to notice is that the null hypothesis always gets the equal sign. And in fact, I don't care if you just make all three of these equal. You can always just use the equal sign in your null hypothesis, and I'm going to be perfectly happy with that. It's this alternative hypothesis that's important to get the sign correct on. All right. Note that it is incorrect to formulate a null hypothesis using the less than, greater than, or not equal to sign. It always, always, always gets the equal sign with it. All right, so we're going to have some steps for carrying out a hypothesis test. We're going to identify the population parameter and the hypotheses. Then we're going to find or formulate our level of significance alpha. That's going to be our cutoff for how much evidence we need in order to conclude the alternative hypothesis. We're going to use the data to calculate the test statistic and the p-value. And we'll talk about what those are in just a moment too. And we're going to draw a conclusion by comparing the p-value to the level of significance alpha. If the p is less than or equal to alpha, you're going to reject the null hypothesis and find for the alternative. If the p is bigger than alpha, you do not reject the null hypothesis. You do not find for the alternative. Make sure that you make a big old note of that decision rule, because you're going to use it all the time with hypothesis testing. Okay? Now, how can you remember which is which? Well, we're going to emphasize what a low p-value means when we talk about it. But in the meantime, I'm going to give you a way to remember this decision rule. Remember, if the p is less than or equal to alpha, we're going to reject the null hypothesis. So if you just say to yourself, if the p is low, the null must go, that will help you out a bunch. And then if the p is bigger than the alpha, the p is not low, so the null does not go. So hopefully that will help you remember the decision rule. All right, big note, the text demonstrates something called the rejection region method for making your decision in a hypothesis test. This is extremely old-fashioned and is not going to be covered in this course. You can skip any sections in your textbook which ask you to do a rejection region method. All right, so let's start with an example. 7.2, formulating a one-sample test of hypothesis. CADSoft, a producer of computer-aided design software for the aerospace industry, receives many calls for technical support. In the past, the average response times have been at least 25 minutes. They want to see if the average response time has been reduced to less than 25 minutes by using a new information system. They collect a sample of 44 response times. So the first thing we need to do is identify the parameter of interest and state our hypotheses. What's our parameter of interest? Well, notice that they're talking about in the past an average response time, and what they're looking for evidence of, again, is average response time. So the parameter of interest is mu. All right, and now we can state our null and our alternative hypothesis. So the first thing you want to do when you're identifying your null and alternative hypothesis is just to write down the symbols that denote each of them. And then I just usually put a colon to kind of represent that my null and alternative hypothesis are coming. All right, so my parameter of interest is mu. The null hypothesis always gets the equal sign, so I can just go ahead and plunk that down. And what's my number of interest? What is the null hypothesis? What do we have no choice but to believe until we find evidence otherwise? Well, in the past, the average response time has been at least 25 minutes. So we're going to use mu equals 25. And if it bothers you not following the exact wording in the problem, you can write bigger than or equal to 25. Either one is fine, equal 25 or bigger than or equal to 25. All right, so now we need to decide what's the direction of the alternative hypothesis. What are they looking for evidence for? What is your research hypothesis? Well, it says here they want to see if the average response time has been reduced to less than 25 minutes. So the alternative is less than. All right. Very good. So we've identified our first set of hypotheses. So now we need to find our level of significance, alpha. So the alpha level is the same concept that it was in confidence intervals. This is often going to be set by some legal precedent or your boss or me. The most common alpha by far, the most common significance level is 0.05. If the level of significance is not stated, you can just go ahead and assume that it's 0.05. Now think about what you use alpha for. You're comparing your p-value to it in order to make a decision about your hypothesis test. So if your p is low, your null is going to go. So if your p-value is low, that means you got a result that's very rare under the null hypothesis being true. And so you're going to start to think that the alternative hypothesis is true. So what the alpha is, what the significance level is a cutoff for how low your p-value needs to be in order for you to go with the alternative hypothesis, for you to make that decision. Okay, it's low enough. So that's what your alpha level is. We're going to come back to this later when we talk about errors in hypothesis testing. All right, so now we're going to use the data to calculate the test statistic and the p-value. For our one sample test for a mean, when you know sigma, we're going to use the standardized version of the sample mean that we talked about in class when we talked about creating a confidence interval for the mean. Except that we're going to specify, just kind of point out that the true mean, remember we're assuming that the null hypothesis is true until we find evidence otherwise, right? So mu, the number that we're going to put in there for that, is going to be the null hypothesized value, the null hypothesized belief of what the true mean is. And then you just take your sample mean minus that null hypothesized belief of what the population mean is, and then divide by the standard deviation of the mean, which is sigma divided by the square root of n. And if sigma is unknown, you know how to play this game. it's the same formula, but we're going to plug in S instead of sigma. And then instead of it being a Z, it's going to be a T distribution. All right. Okay, so in the CADSoft example, sample data for 44 customers revealed. The mean response time, the sample mean, is 21.91 minutes, and the sample standard deviation is 19.49 minutes. And we have our null and alternative hypothesis of mu equaling 25 minutes against mu being less than 25 minutes. And we need to go ahead and compute our test statistic so we can get our p-value. All right, so how do we compute our test statistic? Well, it just told us on the previous page, if we have S instead of sigma, we're going to use that T test statistic. So my T test statistic, I usually put a subscript of an S just to denote that it's from the sample, is going to be X bar minus mu naught divided by S over the square root of N. And what's X bar? It's calculated for us, so 21.91. Minus mu naught, what is mu naught? That's this guy. That's the number that's in your null hypothesis. So here, it's going to be 25. Divided by S over the square root of N. So 19.49 divided by the square root of 44, because that was our sample size. And I'm going to punch this in my calculator and see what I get. 21.91 minus 25 is negative 3.09 divided by 19.49 divided by 'There we go. The square root of 44. And I'm going to close my parentheses and get the answer. It's negative 1.05. All right, so if you punch that in your calculator or Excel, you should get negative 1.05. All right, so now what does that tell us? Well, if you think about standardizing the sample mean, if we had sigma, this would be a standard normal distribution. So this would be interpreted, negative 1.05 would be interpreted to mean that the sample mean of 21.91 minutes is 1.05 standard deviations below average if the null hypothesis were true. The t distribution is fairly close to the standard normal, so you can kind of still think about that as being a standard deviation in your mind. It's not technically a standard deviation, but you can think about it sort of in the same way. So, but how do we turn that into a p-value? How do we quantify that that's very extreme? All right, you know from z-scores that if anything's beyond 3 standard deviations, it's pretty rare, but we need to calculate exactly how rare it is, right? So we're going to calculate our p-value. So we need to calculate this p-value, but what is this p-value? Well, the p-value of a hypothesis test is the probability of obtaining a test statistic that extreme or more in the direction of the alternative hypothesis under the assumption that the null hypothesis is true. When we draw pictures, that definition should become more clear. All right, the p-value is calculated as the tail area quantity in the direction of the alternative hypothesis. For a greater than alternative hypothesis, calculate the area to the right of the test statistic. For a less than alternative, calculate the area to the left. And for not equal, you want to calculate the area in both directions. So I always say, think about it like if you think your neighbor's house on the right was robbed, where are you going to send the police to look for evidence? To the neighbor's house on the right. So look to the right. If you have a less than alternative hypothesis, you think your neighbor's house on the left was robbed, where are you going to get your evidence? To the left, right? To the left of the test statistic. And then for not equal, that means you're not sure which direction it happened in, okay? So that means you don't know whether you heard a noise, but you don't know whether it was your neighbor's house on the left or the right. So the police are going to have to go in both directions to investigate that. So they're going to look in both ends of the distribution. Now, the way that you'll get the p-value in that situation is you'll do the positive version of the test statistic and the negative version of the test statistic, and you'll calculate the area to the right of the positive version of the test statistic and the area to the left of the negative version of the test statistic. All right, so that's how we'll do that. So let's go back to the CADSoft example. Assuming alpha is 0.05, the significance level, and we want to calculate our p-value. So let's draw a picture of our test. I always recommend drawing a picture, especially when you're learning about hypothesis testing. So we've got our t-distribution centered at 0, and remember our test statistic is negative 1.05, right? So now we need to determine what to do with that to get our p-value. Well, our alternative hypothesis, if you remember, the null hypothesis was mu equal 25 or greater than or equal to 25. And the alternative is less than 25. This alternative hypothesis tells you where to shade for your p-value. Just look at your test statistic. You see the direction of the test is less than, so you want to shade the area to the left of the test statistic to get your p-value. Now, this is a t-distribution with 43 degrees of freedom, right? It had sample size of 44. The degrees of freedom are n minus 1. So we can compute that p-value by using the t.dist function. So this is just going to be the t-distribution, t.dist, your number of interest, negative 1.05, and your degrees of freedom, 43. And so we've shaded in the area to the left, and when we put that into our t.dist function, so remember the dot-dist functions calculate the area to the left of something, which is what we want. It's taking the test statistic, the degrees of freedom, and true for cumulative. And we end up getting 0.1498. So what does that mean? Well, that means that about 15% of the time, you're going to see a test statistic that extreme even if the null hypothesis were true. That means that 15% of the time, if you were to get many, many samples, 15% of the time, you would see a sample mean that much lower than 25, even if the true mean were actually 25. So what we found was a pretty common number under our null hypothesis being true, right? But let's be methodical and compare it to our alpha level. Our p-value is bigger, 0.1498 is bigger than 0.05, which is your significance level. So you're going to fail to reject the null hypothesis. Remember, if the p is low, the null must go. If the p is not low, the null does not go. And when we fail to reject the null, that means we didn't find enough evidence to conclude our alternative hypothesis. Okay, so let's try another example from scratch. This one is a vacation survey. A travel agency wants to target a marketing campaign to 35-year-olds. They survey 34 respondents about their number of vacations per year and children. Now notice that your book says they wish to test whether the average age of respondents is equal to 35. This is like saying they're testing for innocence. That is not the correct research question. There are a whole bunch of homework questions that also have the same wording. I will email the publisher and let them know that that needs fixed. But in the meantime, we'll just go on. And it should say they want to test whether the average age is different from 35. So we're tasked with carrying out a hypothesis test at the 5% significance level. Okay, so here we are in Excel. So let's go ahead and start doing these examples in Excel. All right, so first, let's go back and revisit the CADSoft example. We'll just do it one more time so we can fill in our in-class examples worksheet. What was the null hypothesis there? It says CADSoft, a producer of computer-aided design software for the aerospace industry receives many calls for technical support. In the past, the average response time has been at least 25 minutes. And they want to see if the average response time has been reduced to less than 25 minutes by using a new information system. So we'll go ahead and write our null and alternative hypothesis in there. All right, what was our null? Oops, I already have the symbol for the null there. The null is that mu equals 25 or is bigger than or equal to 25, and the alternative, the research hypothesis, the thing they're looking for evidence for, is whether it's less than 25 minutes. All right, and we need to calculate our sample mean, our sample standard deviation, and figure out our sample size in order to plug these values into our test statistic formula. All right, so if we want to get the average response time, we can just use our average function. And I'll just go over here to the data and highlight it, close my parentheses, and we get 21.91 just like we had a moment ago. The sample standard deviation we can calculate with our Excel function. So the standard deviation of the sample, we want to use our column of data again, and we get 19.49, and our number of observations is 44. All right, so we're just filling in the blanks. All right, and what was our null hypothesized belief of the mean? 25, and our level of significance, if you recall, was 0.5. So now we're going to compute our test statistic using Excel. So remember that it is x bar minus mu naught divided by s over the square root of n. So we have our sample mean, which is 21.91, minus the null hypothesized belief of what the true mean is, which is 25, divided by S, which is 19.49, over the square root of 44. And we get negative 1.05. So just use an Excel like a calculator. Now, how do we get that p-value? Remember, when you're getting a p-value, you should always draw a picture. So just come over to the side of whatever paper you're working on and draw a picture of it. It will help a bunch. And remember, the next thing that you do after you draw your picture of your t or your z distribution is to plunk down your test statistic. So I have negative 1.05 is the test statistic. And then you need to decide which way you want to shade. And remember, that's determined by your alternative hypothesis. And our alternative hypothesis is less than, so our p-value is going to be this area. All right, so to get that area in the t distribution, we can use our t dot dist function. And the t dot dist function takes the value you want to look to the left of, so negative 1.0522, comma the degrees of freedom. And remember what the degrees of freedom are? They're n minus 1. Oops. So your t distribution has 43 degrees of freedom because our sample size is 44. And don't forget that you have to tell it that we want the CDF. And we get that 0.1493 again. All right, so what's our decision here? Well, we compare our p-value to our alpha. Our p is bigger than our alpha. Oops, I keep forgetting to grab my pen. All right, p is bigger than alpha. So what do you do if the p is not low? Fail to reject the null hypothesis. So that's your decision. And then what's your conclusion? So fail to reject the null hypothesis. And then what's the conclusion? The conclusion is in terms of the alternative hypothesis. So if we don't reject the null, then we don't find for the alternative. So we're going to say there is not significant evidence at the 5% level to conclude the alternative. And what's the alternative? To conclude the average, what is it, response time or call time? Response time is reduced to less than 25 minutes. All right, so that was our first hypothesis test that we did. Notice that I'm not saying I'm concluding the null. I'm just saying I don't find enough evidence for the alternative. That's a subtle but very, very important detail when you're interpreting these. Okay, so now we can go to our second example, which is our travel agency survey. So a travel agency wants to target a marketing campaign to 35-year-olds. They survey 34 respondents about the number of vacations per year and children, and they want to test whether the average age is different from 35. So carry out the hypothesis test at the 5% significance level. All right, so we need to state our null and alternative hypothesis, right? So what are we looking for here? They're looking for whether the average age is different from 35. So if that's what they're looking for evidence of, which hypothesis is that? Is that the null or the alternative? If that's the one they're looking for evidence of, that's the alternative hypothesis. So our alternative hypothesis is that the average age is different from 35. So that's not equal to 35. And that informs you of what your null is then. Your null then is that the average age is 35. All right, so now we need to calculate our sample statistics. So we want to get the average age from our sample. So we'll use our average function. And we'll take the average of the age column. So we get 36.68. And then we need to calculate our sample standard deviation so we can compute our test statistic. So we want the standard deviation of the sample. And we'll grab our age column. And we get 7.86. And then what are the number of observations? It looks like we have 54, 34. Okay, we have 34. So our sample size is 34. All right, what's our null hypothesized belief of what the mean is? We can see it right here in the null hypothesis. It's 35. What's the level of significance? We were told to use the 5% level, so our alpha is 0.05. And now we have to calculate our test statistic. So what goes into our test statistic? Well, it's x bar minus mu naught divided by s over the square root of n. So it's going to be, we're going to have to enter this in. X bar is sitting up there in the average age box, minus the null hypothesized belief of the mean, which is 35, so 38.68 minus 35 divided by S, which is 7.86. Whoops. Over the square root of n, which is the square root of 34. All right, so let's go ahead and type that in to Excel so we can calculate it. So we want the average age minus the null hypothesized belief of what the average is, divided by the sample standard deviation over the square root of the sample size. And we get 2.73. So now all there's left to do is find our p-value. So again, I encourage you to draw a picture. So let's go ahead and draw a picture here. All right, we've got our t-distribution centered at 0. We're going to plunk down our test statistic, which is 2.73. And we need to know which way to shade. So we need to look at our alternative hypothesis. The alternative hypothesis, however, is not equal to. So this is one of those cases where we want to calculate the area to the right of the positive version of the test statistic and also the area to the left of the negative version of the test statistic, because it's a not equal to alternative hypothesis. So what's our p-value then? Well, it's just going to be this area plus this area. So you could either put in two different t distribution statements, or you could recognize that the area to the right of positive 2.73 is equal to the area to the left of negative 2.73 because the t distribution is symmetric around 0. So I'm just going to calculate the lower tail area and take it times 2. So here goes. I'm going to do 2 times my t distribution, and I want to look to the left of negative 2.73, and the degrees of freedom are 34 minus 1, which is 33. And that should give me, whoops, I forgot to put the true in there. I need to make sure I grab my cumulative distribution function. And that gives me a p-value of 0.01. So, how do we make our decision? Well, we got to compare the p to the alpha. The p-value is 0.01, which is lower than the level of significance of 0.05. If the p is low, the null must go. So we're going to reject the null hypothesis. And if we reject the null hypothesis, did we or did we not find significant evidence for the alternative? If we reject the null, we do find significant evidence for the alternative. So there is significant evidence at the 5% level to conclude what? The average age is different from 35. And that's our second hypothesis test. So hopefully you're starting to get a feel for it and get the hang of it.